Hello everyone, my name is Shayanan, and in this video I'm going to tell you briefly about an interesting phenomenon called the quantum Hall effect in graphene. So let's first start with the basic. What is Hall effect? So Hall effect was first discovered by Edwin Hall in 1879, and the experiment is set up as follows. So let's say we have a thin piece of semiconductor with electric current passing through it in x direction. It is also subjected to the magnetic field in perpendicular to the current, and in this case in z direction. And due to this applied magnetic field, the electrons and holes flowing in the semiconductor now experience a magnetic force, which causes the buildup of negative charge on one side of the semiconductor and the positive charge on the other side. This net charge then induces an electric field in the y direction, which consequently produces the voltage across the semiconductors. This voltage is called the transverse voltage or the Hall voltage. The resistivity and conductivity of the semiconductor can then be determined. So first we need to consider the motion of the charged particles in the system, which can be expressed as shown. And in steady state, the force acting on the particle are balanced out and dV over dt becomes zero. We then get the following relationship between the current density and the induced electric fields as shown here. And since the current density is equal to the conductivity times the electric field, we can get the expression for the longitudinal resistivity and the transverse resistivity as shown. And you can see that the transverse resistivity ρxy depends on the electron density of the sample and the applied magnetic field. So if we plot the graph of the transverse resistivity against the applied magnetic field, we will get the linear relationship. On the other hand, the longitudinal resistivity ρxx is constant, as it is independent of the magnetic field. So next question, what is the quantum Hall effect? So as we already know, the quantum refers to the smallest possible discrete unit of any physical properties. So this concept also applies to this quantum Hall effect. Quantum Hall effect was first discovered by Klaus von Kliesing in 1980, and the setup of the experiment is similar to that of the classical one, but with the two-dimensional electron gas system as a sample instead. So the 2D EG system is a scientific model of an electron gas that is free to move in 2D plane, but tightly confined in the z direction. And this system can be formed at the semiconductor surface, as in the case of the silicon MOSFETs and the gallium arsenide, aluminum gallium arsenide heterostructures on the right. As you may notice, although this structure can be much thinner than the semiconductor piece that we use in the classical experiment, this structure still has the active regions for electron conduction that are hundreds of atoms thick. So this system is often regarded as a quasi-2D EG system instead. And when we subject this system to the strong magnetic field and very low temperatures, the transverse resistivity and the longitudinal resistivity begins to deviate from the classical result. The transverse resistivity now forms a plateau where the resistivity stays constant over a range of magnetic field at the value of h over n e squared, where n is an integer of all the fractional values. On the other hand, the longitudinal resistivity vanishes to zeros whenever the transverse resistivity sits on the plateau, and it spikes when the transverse resistivity changes from one plateau to the others. This quantized Hall resistivity led to the establishment of the new metrological standard, as this standard quantum resistor h over e squared contains only fundamental constant of electron charge and the Planck constant. So now let's consider the energy levels of electrons in the quantum Hall effect. Under the magnetic field, we can write the Schrödinger equation of the electrons as shown here, where A is the potential vector that gives rise to the magnetic field, And by choosing the coordinates such that the vector potential Ay is equal to minus Bx and Ax is equal to 0, the Schrödinger equation can be simplified to a one-dimensional harmonic oscillator problem. And we can solve this equation to get the energy levels of electrons as En equal to h bar omega times n plus 1 over 2. And this is also called the Landau's levels of energies. And as you can see from the equation, the Landau's levels from the quantum Hall effect is equally spaced with the energy difference between each levels equal to h bar times omega. So now what if we can create a nearly ideal 2D EG system and subject it to the quantum Hall effect? What will the result be? This question had led to the study of the quantum Hall effect in graphene. So graphene consists of an isolated single atomic layer of graphite tightly packed in a honeycomb crystal lattice. So it is an ideal realization of such a two-dimensional electron gas system with only one atom thickness and no intrinsic volume. And considering the band structure of the graphene, unlike the parabolic dispersion relation in other 2D EG systems, the carriers in graphene exhibit a linear energy dispersion relationship in the low energy spectrum region near the direct points. And when subjecting the monolayer graphene in the magnetic field, the Hamiltonian operator of electron can be modified as shown here. By solving the Schrödinger equation, we then get the energy level of electrons in graphene, which is proportional to the square root of integer n. And this results in the unevenly spaced in energy of Landau's levels you can see in comparison with the Landau's level of the conventional 2D EG system. And you can also see from the picture on the right that there is a large energy gap between the first two Landau's levels of electron in graphene. And this allows the quantum Hall effect in graphene to be observed at much lower magnetic fields and all much higher temperatures. And as a result, this graphene can even be observed at room temperature, and the result is shown in this graph here. And from the calculation of Landau level of graphene in the previous slide, we can see that the total degeneracy of the graphene is equal to 4 at each energy levels. And this led to the unconventional half-integer quantum Hall effect, as the sequence of the plateaus of the transverse conductivity was displaced by a half-integer multiple of 4. This property of quantum Hall effect in graphene has opened up a new prospect for developing graphene-based resistance standard and for novel quantum devices working at elevated temperatures. I hope this video helped you with the understanding of the quantum Hall effect in graphene. Thank you for listening.